Good evening, everyone. Hi. Welcome to the Spring 2025 Vernon Lecture. For those of you who don't know, the Vernon Lectures are held twice a year in memory of Ace Vernon, who was a member of the Board of Trustees at Mount Cuba Observatory. And he was very interested in just learning things and spreading knowledge to people. And so this lecture series is an attempt to keep that going. Tonight we're very happy, and I had to write a whole page. I'm not going to tell you this whole page, but we're very happy to have Konstantin Batygin. I think, did I get that right? Close enough. He's from Caltech. He started his academic career actually at UC Santa Cruz, where he started working on planetary evolution. And after he graduated from Santa Cruz, he went to Caltech and has stayed there. You're still there. Yeah, you're the professor of planetary sciences at Caltech. And he's interested in planetary science and looking for Planet 9. There's a couple interesting things, though, that you should know. First of all, he's the head of technology at Lucentic, which is an AI company. And he's also the lead guitar and singer for a band. Yeah, so maybe. The 7th season, so I think you're doing a new album, you told me, right? Yeah, so look for an album coming out from the 7th season. So I'm going to turn it over to him now, and welcome. Thank you very much.
Thanks very much, Judy. It is true, our band is coming out with a new album, and our monthly Spotify listeners will probably diminish even further, okay, from 39 to 29 or something like that. Yeah, so, it's a real pleasure for me to be here. Over the last 3 decades in astronomy, we've had quite a remarkable set of discoveries, right? The discovery of gravitational waves, for example, the large-scale characterization of the galactic planetary census of planets around other stars. And it's really a wonderful time to be alive, right? To kind of live through this revolution. And in parallel, over the last couple decades in the solar system, we've only been losing planets. Okay, like Pluto got demoted in 2006. We went from 9 to 8. So a project and a theme that's been central to my own work over the last decade or so, together with my partner in crime, Mike Brown, also at Caltech, is to kind of restore the solar system to its 9-planet glory and make it great again. Okay, like that's what this is all about. So I'm going to tell you guys a little bit about that. So let's begin with a brief outline of the architecture of the solar system. So we've got Mercury, Venus, Earth, my house right there, Mars, Jupiter, Saturn, Uranus, and Neptune. And second, Pluto will appear. And even though we have not discovered any new planets in the solar system since 1846, what we have discovered over the last 3 decades is the existence of a field of icy planetesimals, icy asteroids, that live beyond Neptune. Now, a lot of people are, of course, familiar with the asteroid belt between Mars and Jupiter. Turns out the solar system also has a second icy asteroid belt called the Kuiper Belt, which is much more massive and much more extensive, and lives, beyond Neptune, forming this donut. In fact, I have been trying to get people to rename this into the Dunkin' Donut, because the person who actually predicted this was Martin Duncan, right? Kuiper sort of speculated about it, but Martin Duncan actually got it right. This is like a joke that only makes sense on the East Coast, right? It's great. So the discovery and the characterization of the orbital structure of the Kuiper Belt has largely rewritten our understanding of the early evolution of the solar system. And perhaps the first and basic question you can ask is, why is it there? Like, how did these icy planetesimals get there? They're all on eccentric orbits, as you can see, and some mechanism is necessary to emplace them into their current orbital neighborhood. They did not form where they are observed. And this has led to the realization that the planets themselves, the giant planets of the solar system, themselves have not always occupied the orbits that they occupy today. We now know that Jupiter, Saturn, Uranus, and Neptune started out in a somewhat more compact orbital configuration and were encircled by a disk of icy planetesimals totaling as much as 20 Earth masses outside of Neptune's primordial orbit. And as the planets kind of ground through this primordial disk, by scattering planetesimals all over the place, the solar system underwent this period of instability. Okay? And then eventually, through the process of dynamical friction, the planets settled onto their present day wider, kind of nearly circular, nearly coplanar orbits. And this class of instability-driven models are cumulatively known as the Nice model, not just because it's a nice model, but also because this class of models was developed by a group at the Nice Observatory in the south of France. And within the context of this picture, you can understand the present-day observations of the Kuiper Belt as just being the remainder, that last 0.1% of the icy planetesimals that the solar system had to start with. Yes?
So I saw all these things you're shooting out. Is that just from the gravitational slingshot effect?
Yes. Yeah, this is
Everything off into...
exactly. Yeah, this is just this is the starting point of this simulation that you just saw was, you can think of it as the moment when gas evaporated from the solar system. Now you can think of that as 3.8 million years after formation of the first solids. Okay, so gas is gone, now gravity is the dominant effect, and because you have a n-body problem where the n is very large, the evolution is both chaotic and kind of dissipative in the sense that you're throwing away a lot of material. So you're lowering the energy of the cumulative system while losing mass. And the effect of that is spreading. Okay? Great question. So the details of this class of models have been worked out in kind of, I have no other way to say it other than a remarkable amount of detail over the last 15 years. And we now know a lot about Neptune's migration history. But one of the things that the Nice model, and in fact any kind of formation model, cannot explain is why, if you go and look far enough away, right, focus on the most long period orbits that we know of in the solar system, and now for scale, Neptune's orbit is now inside of this white beam. Well, if you go and look at orbits that take 10,000 years to go around the sun once, you see that they all kind of lie in a common plane that's tilted by about 20 degrees with respect to the ecliptic plane, and they all kind of point in the same direction. And this is something that we pointed out in 2016, inspired by work of our colleagues, Chad Trujillo and Scott Shepard. In fact, we're in Delaware, so I have to make a Joe Biden joke. And this object right here is called Joe Biden, okay? Because when you discover a Kuiper Belt object, it gets a license plate, and this one got the license plate VP113. Joe Biden was VP at the time. And so it became this kind of long-running thing, like, okay, we have Sedna over here, and we have Biden over here. Okay. So this pattern of orbital alignment has sort of been reinforced over the last decade. So this is now a plot from 2017. You can see more orbits have been discovered by then, right? 2019, right? More orbits still. 2021. Right? And this is more or less what the present day observational census looks like. And what you see is not just that the orbits cluster together, but the degree to which they're grouped correlates strongly with their orbital stability. Let me expand on that for a second. The orbits that are labeled in purple here are the ones where if you were to take this picture and let it go, right? Let time evolve forward, not much would happen to them, right? They would just their orbits would slowly precess around the sun, but they wouldn't go away. Conversely, the green ones are the ones that interact with Neptune so strongly and so chaotically that they're on their way out of the solar system. If you wait long enough, and long enough here is not that long, it's only like 50 million years, right? Then they're going to be out of the solar system. So you can think of the green subsample of the objects as being contaminated by chaotic dynamics that arise from Neptune's gravitational scattering. The purple guys are the stable things that can have a footprint of what else is out there. Okay, so this is what you got. Like, this is what the outer solar system looks like. Why is it like that? Why is it clustered together? The first temptation, always, is to ascribe anything we see in the solar system to some event that happened 4.5 billion years ago when the solar system was just forming. Say, okay, well, I don't know, something bad happened to the solar system, like a star flew by or something, arranged the orbits, and that's why we're seeing this pattern today, right? Turns out that explanation does not work. Okay, it does not work because each of the orbits is a different size. And so if you were to let them go, in a few 100 million years, this pattern would disappear, okay? Because each one of them would precess at a different rate. So it's like having different hands of a clock, right, that each go at different rates. So if you really believe in what you're seeing, you believe in this clustering, then this is telling you that something is keeping the orbits together. Something gravitational is keeping the orbits together, like right now. Okay? So what can it be? In fact, in order to break the symmetry, you have to introduce whatever that is, has to orbit on an eccentric trajectory, an elliptical trajectory. So we've done many, many simulations, and here's what we found. Turns out the way to reproduce these data is to introduce an additional planet into the outer solar system, shown here as this big purple ellipse. This is the orbit of planet 9. For scale, this little pink circle in the center is the orbit of Neptune. In this simulation, planet 9 is on an orbit that takes about 20,000 years to go around the sun once. Scale, this aphelion, this is about 1,000 times the distance between the Earth and the sun. And what you're seeing right now is the evolution of the gravitational evolution of the solar system, starting at the end of the Nice model, where the Kuiper Belt gets created, initially in a completely random, right, axisymmetric way. But over time, through gravitational interactions with planet 9, as well as scattering interactions with Neptune, a pattern slowly begins to emerge. And that pattern, which becomes apparent right about now, we're about 2.5 billion years into the lifetime of the sun right now, right? You're starting to see maybe that the surviving objects, surviving orbits are anti-aligned with respect to the orbit of planet 9. Like, you guys are seeing this too. Yes, okay, I'm not alone. All right, good. All right, so like, what's going on? Why is it doing that? Well, the answer actually is in the fact that when some of these objects precess through orbital alignment, you can actually see it in the simulation, the eccentricity, ellipticity goes through a peak. And what this does is it jams the perihelion, the closest approach to the sun, into the orbit of Neptune, and Neptune scatters these things out. So the fact that you survive on the opposite side is closely correlated with orbital stability. It's not that the planet is kind of a mother hand that gravitationally keeps everything together. It's that the planet causes orbitally aligned things to go away from the solar system. Okay? And in order to reproduce the degree of clustering that we see, the onset of clustering that we see, you need an object. Okay, this planet needs to be about 5 Earth masses and has to orbit on an appreciably inclined orbit, about 20 degrees, with respect to the plane of the solar system. and has to have an orbit that is eccentric, right? Think about 30% out of round for typical calculations, and a orbital period of 10 to 20,000 years. The other thing that I will maybe draw attention to is that an inescapable consequence in all of these calculations is that we also generate bodies that come out of the plane of the solar system. Okay, just like this is weird, right? So just remember that, okay, because we'll come back to that in a little bit. Okay, so maybe I have convinced you, right, with this sales pitch, but if you're a skeptical person, you might say, but hold on. What if, like right now, it's kind of fashionable to talk about a deep state conspiracy, right? So what if this is like a deep state conspiracy, right? Like, how do we know that this effect is actually real and not a consequence of observational bias? This is an important question. It's an important question because, as you can see, all of these orbits are highly elliptical, okay? If you're trying to find something in the outer solar system, it helps if it's closer to the sun. In fact, it helps by a power of r to the fourth, okay? And so you're heavily biased to finding these bodies when they're at perihelion. Now let's imagine a pathological astronomer that has a favorite part of the sky, okay, and only looks in that part of the sky, right? If you do that, you're going to only find objects that are close to perihelion in that part of the sky, and through just survey strategy, you can create clustering, okay? And this has been, this has been a question that has really lingered for a number of years in the literature, like, to what extent do we know that this degree of clustering is real? So the answer is that there is a chance, okay? There is a chance, and I want to be honest about it, that this is fake, okay? And that chance is about 0.2%, okay? So that's what you have to gamble with, right? One in 500, okay? And the way you can calculate this is to say, well, we actually have a footprint on the night sky of where Kuiper Belt objects, these distant Kuiper Belt objects, have been discovered, right? So we kind of have an idea of where people have looked for them. And by modeling what the kind of observability map of each of these distant Kuiper Belt objects is, you can ask the question in a rigorous way, what is the number of times you would see the degree of clustering that we see by chance? And cumulatively, it's about 0.2%. Okay, but that's only one line of evidence, right? I asked you to remember this thing that's popping out of the plane of the solar system. In fact, this is a very robust outcome of all Planet 9 calculations we've ever done, even when we fail to match, even if you choose parameters incorrectly, and you fail to match the degree of orbital clustering in the population we discussed up until now, one of the inescapable consequences is that you puff up and excite high inclinations in the outer solar system no matter what. And this is not something that can happen naturally when you just form a planetary system, right? Like planetary systems form in disks of gas and dust that are rather plain. So we thought this would be, even like before we detect Planet 9 directly, this would be a good prediction that we could make. We could say, if Planet 9 is there, then inescapably, you should have objects that are strongly misaligned with respect to the plane of the solar system, and that could be an indirect additional line of evidence. Now, we thought this would be a great prediction because most of the time when people look for stuff in the solar system, they look along the ecliptic plane, along the plane, because you don't want to spend your time staring into darkness where there's nothing. So we kind of said, well, maybe there is something there. Turns out, not only is this prediction true, this prediction is in fact a retrodiction because such objects, by the time we made the prediction, were already discovered. And they were discovered by the WISE survey, which was a survey that looked principally for asteroids and stuff. And they were already sitting in some data set. Okay? We just had to kind of dig them up. And so as far back as many years ago, it turned out the solar system really does have this population of long period things that orbit almost perpendicularly to the plane of the solar system, and their orbits are very long, right? Kind of in the same orbital range as the cluster that we've been talking about up until now. So we thought, okay, this is getting interesting, okay? Like, so far, reality really matches the expectations that we see from theory. Okay. Then some time passed. Oh, I should say, this is, by the way, what the census of these highly inclined objects looks like now. There's now about 20 of them and counting. Okay. Then some time passed, and this was discovered. Okay, so this is, again, for scale. Jupiter, Saturn, Uranus, Neptune, and this object was discovered right here, okay? And it orbits in a perpendicular way to the plane of the solar system, but it's not, right? It's not anywhere in the range of orbital periods that should have been affected by Planet 9. In fact, this thing is parked right next to Neptune, right? And we thought, well, what's going on with this? Like, out here, you're completely dominated by the gravitational interactions with the giant planets, not with Planet 9. So how can we understand the existence of this? And in fact, is it even connected? Well, if you remember back to the first, or rather second simulation that you saw, right? The one where all the orbits started out in a disk and then they were dancing around and a pattern carved out. There are fewer orbits in the end than we started with, right? Many of them went away. And I described how when they go through orbital alignment, there are scattering events, and Neptune gets rid of them. Well, scattering is a somewhat symmetric process. Sometimes you get scattered out by Neptune. Other times you actually get scattered in. So if you keep track of what happens to those orbits, okay, those unstable guys that are going in, here's what you see. Okay, so once again, these are orbits of Uranus and Neptune for scale. This is the orbit of Planet 9. We saw before. And here I focused on a single particular Kuiper Belt object in our simulations, which evolves in this interesting flipping way as I talked about, right? It's trading its eccentricity for orbital inclination and coming back. And when it hugs the orbit of Neptune, Neptune changes its semi-major axis through gravitational scattering. And so in this particular simulation, right, this object at the end of the solar system's lifetime comes in and parks in this perpendicular manner, right, perfectly hugging the orbit of Neptune. And this is, nature's way of telling us, like, if you liked it, then you should have put a ring on it, okay? Like, that's what's going on here, okay? And so we thought this is like kind of remarkable. The pieces are kind of starting to fall together. And once again, it turned out that this object was just the tip of the iceberg. It turns out there's a whole population of these guys. And because I've shown you already too many good movies, okay, I should just show you a plot, okay, just to, I don't want to get you guys overexcited. You can go back to sleep like this, okay? So this shows that population of these close by retrograde and highly inclined bodies. So here on the y-axis is the orbital inclination. So here you're perfectly in the plane of the solar system. Here you are orthogonal to the plane. Here you're anti-aligned. You're orbiting the sun in the wrong direction, so to speak. And the semi-major axis range goes from 30 astronomical units, where Neptune is, to 100, right? So this is really proximity to Neptune. This right here is the regular Kuiper Belt. See, as you can see, there's a whole population of these guys. And this is a version of the same plot where on the x-axis, I'm plotting not the semi-major axis, not the size of the orbit, but the perihelion distance, the closest approach. And in the background, this green 2D histogram is where in Planet 9 simulations objects end up, and the dots with the blue halos on them are the real observational data. So really, the union of these plots kind of tells you that the observed population kind of ends up where the theory predicts them to be. If there is no Planet 9, all you can do is about 30 degrees. Right? Anything above 30 degrees requires an additional excitation, whether it be Planet 9 or whatever other mechanism you create. Okay? Something needs to happen to raise the inclinations higher than 30 degrees. That's the number to keep in the back of your mind. Okay. So if we are to sort of think through and maybe summarize the lines of evidence that we discussed up until now, they're kind of four, right? Line of evidence one is that the orbits, the very distant bodies, are all pointed in the same direction. Line of evidence two is that those same objects are tilted into a common direction, right? So you can think of it as their eccentricity vectors and their angular momentum vectors are all grouped together. Line of evidence number three is that also, if you keep looking far away, right, you will find objects in the outer solar system that are very high semi-major, very, very elongated, that are tilted with respect to the plane of the solar system by a large angle. And number four, these objects come in and pollute the more inner part of the solar system with retrograde bodies. That's kind of what we've discussed up until now. And I've kind of felt frustrated over the last 5 years at the fact that there are only four lines of evidence. Like, I felt like if there's a planet, there's a bona fide planet in the outer solar system, there should be more than four things that it does, okay? Like, four is almost infinity, but not quite infinity, I don't know. So over the last 5 years, we've been trying to find more evidence for this thing, and it's been tough. So the first place we looked is we thought, okay, maybe there's a deficit of our calculations, and that deficit is that our calculations treat the sun at the center, draw a box around the sun that's, a few tens of thousands of astronomical units, and don't consider anything else. But the sun did not form in isolation, and maybe thinking through better how the sun formed would lead to some kind of an additional line of evidence. And here's why we think it's important. Okay? So this is a picture of the Orion Nebula. Okay? There's a bunch of stars here. Cumulatively, there's about 3,000. And we think the sun formed in a cluster of stars quite similar to this. Okay? One of the simplest lines of evidence for this is the fact that if you go and pick up a meteorite, you can ask the meteorite, how much aluminum-26 did you have? And the meteorite will answer, I had a lot. Okay? And the fact that it had a lot of aluminum-26 requires some kind of pollution of the protosolar nebula by either a supernova or more likely a Wolf-Rayet star. Okay? So that in order for the primordial solar system to get polluted by aluminum-26, you need it to be in a cluster, almost certainly. And like, in general, stars form in clusters. So this is nothing surprising about that. So let's think about the consequences of that. Let's imagine first that we have both the formation of the solar system in a cluster, and you believe that Jupiter and Saturn are really there. Okay, like try to like hold these two things in mind. If you believe those things to be truly there, then an inescapable consequence is that as Jupiter and Saturn undergo their runaway accretion cycles and become big, they throw away a lot of material. Like they scatter rocks outwards. And if you have a model of the solar system where the sun is at the center and then there's a box and nothing else, then these rocks just get ejected and nothing else happens. But if you embed the solar system into a cluster, then you also have the cumulative kind of potential, gravitational potential of the cluster, as well as passing stars flying around. And what these passing stars will do is they will occasionally briefly tug the orbits and change their orbits such that they get decoupled from Jupiter and Saturn, creating this kind of quasi-spherical halo of material at a scale of about 1,000 to 10,000 AU. I did not come up with this. It's called the inner Oort cloud, which is genetically different, we think, from the regular Oort cloud. It's confusing because they're both called the Oort cloud, but bear with me. So if this is an inescapable consequence of the existence of Jupiter and Saturn and the fact that the sun formed in a cluster, then that's what we've got. And observationally, we'll never see it, okay? Because these objects are so far away, you need a telescope like the size of the Earth's orbit to find them. Not really that big, but it would help. Okay. Now, if Planet 9 is there, okay, because it occupies a similar orbital range, then Planet 9 over billion-year timescales can kind of unfreeze these orbits and dynamically send some of them back into the solar system. So we thought, what if we could find some interesting pattern in the simulations, which would lead us to kind of make a prediction about what this population of inner Oort cloud objects coming back into the solar system would look like. So during COVID, we built a model of the outer solar system as perturbed by the cluster. That model is summarized on these plots. You don't really have to read them, okay? And then we ran the output through these evolutionary calculations as we've been discussing, as we've been doing, to look for what changed. And the unfortunate answer is that statistically, nothing changed. Okay? Turns out, if everything I told you up until now is true, the objects that are coming in from the inner Oort cloud would cluster in statistically the same way as the long-period Kuiper Belt objects. And unfortunately, the Kuiper Belt objects do not come with labels. They don't say, oh, I came from the inner Oort cloud as opposed to I was ejected by Neptune. And so we can't really tell. Like some of those objects that we're observing might have been sent in by Planet 9 from outside in. Some of them were ejected out by Neptune. We don't really know which one is which, okay? And it doesn't matter. So this is like observational. I mean, we wrote a paper and everything, but like this falls short of being a new line of evidence because it's indistinguishable from what we've been talking about before. Okay. But then we did actually find something. Like if we had found nothing, I wouldn't be telling you about a new line of evidence. Okay, so like we did actually find something last year, which is pretty interesting. Okay, so going back to this plot, right? Remember how I told you, oh look, only the stable things cluster together, right? Only the things that are not messed up by gravitational interactions with Neptune are the things that can retain a footprint of Planet 9-induced evolution. And the highly unstable orbits are not that important, okay? So we thought, okay, let's revisit that assumption and look at what the highly unstable orbits are doing. In fact, let's not just do highly unstable orbits, let's look at the most unstable orbits that we can think of in the outer solar system. And those are the orbits that don't just touch the orbit of Neptune, but cross it. Like if you cross the orbit of Neptune, you're being messed up by Neptune's gravity and you're on your way out. So First, we consulted the simulations. And in the simulations, we found that if Planet 9 exists, it should drive a continuous flux of Neptune crossers. Let me expand on that a little bit, right? Imagine you start out with a population of long-period icy planetesimals that all cross the orbit of Neptune. And then you let time go forward. In 50 million years, Neptune scatters them all away. And now the population of Neptune crossers is basically zero, right? We've cleared it out. If Planet 9 is there, though, on the other hand, it keeps sending them in through its gravitational effect. And that's shown in this middle plot, where the time of the age of the solar system, lifetime of the solar system, is plotted on the x-axis, and the perihelion distance, the closest approach to the sun, is plotted on the y, with Neptune, Uranus, and Saturn shown here for reference. And you can see how, right, if Planet 9 is there, these distances oscillate until they cross the orbit of Neptune. And through this mechanism, you should establish a continuous kind of existence of this population. Then we did some more sophisticated calculations. In fact, these are probably the most sophisticated calculations ever done of the evolution of the solar system, because they begin with the Nice model, as I showed in the second or third slide. So they begin with kind of evolving the giant planets outward, self-consistently accounting for how the Kuiper Belt gets created, self-consistently accounting for the evolution of the sun in the cluster. Then the cluster of stars goes away, and then we self-consistently calculate the evolution of the outer solar system subject to both the gravity of the giant planets as well as the gravity of the galaxy and the effects of passing stars. So there's like kind of nothing left, okay, to include these calculations. So we did two, okay? We did one with Planet 9 and one without. And these two plots summarize the answer, where on the y-axis you have perihelion distance. That's the distance of closest approach, again, to the sun. So for reference, Jupiter is here at 5, Saturn's at 10, Uranus is at 20, Neptune's at 30, okay? And the semi-major axis here is well in that outer solar system regime. So 100 AU to 1,000 AU. And so this one includes Planet 9, this one does not. What you see is that if Planet 9 is absent, then all the bodies that cross the orbit of Neptune barely do so, right? As they kind of diffuse inwards, they don't have much time before they're ejected out. And so you would imagine that this would create a heavily concentrated population of objects that at best cross the orbit of Neptune by a little bit. Conversely, if Planet 9 is there, then you create rather smooth distribution of perihelia, right? Like these objects not only cross the orbit of Neptune, they keep going until basically they hit the gravity of Saturn, okay? So this is a real distinction that we can go and look for in the real data set. So we looked, and here's what we found, okay? So on the left-hand side, here we have a diagram of the current census of well-quantified orbits of Neptune crossing Kuiper Belt objects. And on the y-axis, sorry, on the right-hand side, we have the same plot as we saw before, only this is now real data, not theory. Okay? So I think you can decide for yourself if these points are heavily concentrated at 30, as would be the case if Planet 9 was not there, or if they are spread rather uniformly, as would be expected if Planet 9 was there. So I'll show you again for comparison, right? This is what you would imagine if Planet 9 is not there. This is what you imagine if Planet 9 is there. I would argue it's pretty broad, okay? In fact, we have to be careful, okay? Like before we congratulate ourselves, we have to be careful because there is, once again, the question of observational bias, right? I talked about how observational bias makes it so that things that come in closer to the sun are easier to discover, right? So to some extent, even if you were to have a population that's quite confined to, say, 30 AU, you would stretch it out in the observational data set a little bit by the action of observational bias. But the good news is we know how to account for that, right? That's not like a mysterious mathematical factor. That's a very well understood mathematical factor. And so upon accounting for that factor, what we find is that this population of Neptune crossers rules out the non-existence of Planet 9 at more than 5 sigma. And conversely, the Planet 9 inclusive simulation is indistinguishable from the data. Okay, so the present day observations really, really disfavor a Planet 9 free solar system. By the way, this was the first time in my career that I had to remember that if you multiply a bunch of logs of a random number between 0 and 1, you get a Gaussian distribution. Like I remember learning this in an undergraduate class and thinking to myself, this is the most useless thing in the world. Like when am I ever going to first generate numbers between 0 and 1, then take their logarithm and then multiply them together? Like this is, but okay, it came back to haunt me. Okay, so all of this, as you can tell, is based upon data sets that are not in the hundreds, right? Each line of evidence has kind of 10 or 20 objects, right? Ideally, we would like to test all of this independently, and we would like to know more. In most work on theoretical astrophysics, you say, I have a prediction. It might get tested 200 years from now. I don't care, because I won't be around to find out if I'm wrong or right. This is not the case with Planet 9, right? Planet 9, like we're kind of gonna know maybe next year, okay? Because LSST, the Vera Rubin Observatory, is coming online this summer. It's been under construction for some time, right? This is an NSF-funded project in Chile, and this is not like a ChatGPT generated fake picture of it. This is a real picture of what it actually looks like. In fact, looked like some time ago. And this telescope is unique in that its entire job is to wake up every night, open the shutters, and kind of look left and right. And then the next night, it does that again, and it does so indefinitely. Okay? And all the data becomes immediately public. So there is a good chance, I would say, that Planet 9, well, there's a fair chance that Planet 9 just gets detected by this within the next couple of years, and we're just going to know. Even if it doesn't, we will know through an independent survey all of the kind of indirect lines of evidence that I covered in this talk, and they will either get confirmed or they will get refuted. One way or another, there will be an observational resolution to this problem. And even though Planet 9 has not been observationally confirmed yet, my friend Eduardo Martorell, who is the conductor of the Miami Symphony, wrote a remarkable kind of 19-minute long piece about Planet 9. It sort of has a time signature, but like kind of not really. And we performed it once live in Miami in 2018. And then 2019, and then we were gonna perform it on Einstein's birthday, again, on March 14th, 2020. And I don't really remember what happened, but we couldn't do it. So we had to do it remotely afterwards, which is why the symphony are all wearing masks and are in Miami, and I'm just at home next to my board. And so the other thing that was kind of cool is through a mutual friend, we were able to, after we recorded it, we called the International Space Station, where Soichi Noguchi, the Japanese astronaut, was floating around. And we played him the recording, and he listened to it and politely said that he liked it. But the comment section of YouTube, okay, also had opinions. And David Gertzman says that this is dripping with the usual self-importance and arrogance one can always expect from composers and musicians. But other than that, it was okay. Okay? And Smokey McPot says that this is bizarre science, Planet Nines, meets pseudoscience, face veils. Okay? So Smokey McPot is unvaxxed, unmasked, unafraid. Okay. I think I'm starting to run over time, so I will stop here and take any questions. Thank you. Yes.
Are you familiar with the term Kuiper Cliff?
Am I familiar with the Kuiper Cliff? Yes. So would you like me to elaborate? Okay. So the Kuiper Cliff is the observation that the conventional part of the Kuiper Belt, that first halo of orbits, appears to end at about 47 astronomical units, and that corresponds with an orbital period with about twice Neptune's orbital period. And so the question is, are those two things connected? For a long time, people thought they were. I don't actually think they are. What I think happened is that the solar system, okay, like the solar system had to end somewhere, and particularly the solid component of the solar system had to end somewhere. And as we now understand, in order to create planetesimals, in order to create these icy asteroids, you need an overdensity in the midplane of the disk. And such overdensities can only happen, close enough. That number for the solar system was probably about 50 AU. So the cliff is probably not so much of a cliff as it is a fall off where the solar system's, solid component ended. And the fact that it happens to be close to Neptune's 2-to-1 resonance is interesting, but it might also be kind of a little bit of numerology, where if you were to imagine that it happened somewhere else, you could come up with a different integer, like 13/6, or something, 14/6, right? Some other number. And these resonances permeate the outer solar system. So yeah, I think the Kuiper Cliff, I've thought a lot about the Kuiper Cliff, especially as a graduate student, and I kind of convinced myself that it's not a big deal. I might be wrong. Yeah. Yeah. Yes.
Has the James Webb telescope influenced or informed your research at all? Fairly recently coming online, and I don't know if it's
Yeah.
towards your Planet 9 or...
Yeah, it hasn't yet because we don't know where it is. So James Webb is an excellent characterization telescope. It's got a tiny field of view, and what it does is it looks at stuff in infrared. So when we find it, right, we will absolutely observe Planet 9 with James Webb. We're going to hit it with everything, right? But James Webb is definitely one of the things we're going to hit it with to understand the spectral composition of the atmosphere, et cetera. That said, James Webb is not a good survey telescope, right? You're not going to kind of look for stuff with a sniper rifle, right? You want to look for stuff with a larger field of view. So the survey that we did conduct, we conducted with the Subaru telescope, which is the Japanese National Observatory. Subaru has a much larger field of view. But what we found, well, okay, I'll tell you my experience. What I found is that I don't actually like observing that much because you have to stay up all night for the wrong reasons, okay? The telescope breaks all the time, okay? There's like clouds that get in the way. Sometimes the atmosphere just goes turbulent. So you're completely not in control. It's very different from doing theory. Theory is great. You relax at home with a glass of wine, write some equations, right? It's fun. So The other reason we, aside from that, the other reason that we haven't found Planet 9 is that our survey has just been very inefficient. And by what I mean by that is in order to detect Planet 9, you need 3 consecutive detections, right, to tie together a line of observations. The number of times, and oh, by the way, Planet 9 is up in sort of the December sky in the northern hemisphere. So the weather is bad, and the number of times we actually had a good run were for 3 days consecutively, we were able to observe well, especially given that you only get 3 days per year, has been limited, okay? So we eventually, like, right around the pandemic, we just gave up. We thought this is a task that is much better left for LSST to just do its thing, because even if LSST loses a day or loses 2 days, it doesn't matter because it does the same thing night after night. So it's a very high efficiency survey. So LSST might not get Planet 9 because Planet 9 might be too far north, or it might be slightly too dim for LSST to get it, but at least we will know, we'll have a good idea of where it is not. Okay? And once we have a good idea of where it is not on the night sky, we can do a much more targeted search. That was a long answer. I think I gave you more than you were looking for, but I am not sorry. Any other questions? Yes?
Yeah, the Neptune crossers that Planet 9 apparently makes happen, I guess is the way
Yeah.
to say it. Normally, if that's the word, Neptune crosser, if you're crossing Neptune, you're going to get ejected. Does that happen with Planet 9 in the story?
Yes, it does. Yeah, so in fact, you can think of the population of Neptune crossers, the specific ones that we see, as a transient population that's continuously being replenished, right? Some of them just get scattered out and become, interstellar objects. Others actually get scattered in, they become Jupiter family comets, right? They make it all the way down to Jupiter, right, and then get activated. That's actually where Jupiter family comets come from, right? That's why we haven't run out of Jupiter family comets yet. So yes, that process does happen, but before it happens, they get a chance to develop a smaller perihelion distance than they would otherwise. If not for Planet 9, they would all kind of get stuck at the Neptune barrier, and only a tiny fraction would make it in, and the tiny fraction in absence of Planet 9 that makes it in, it's actually quite fascinating, are super long period bodies that get twisted up by the galactic tide, and then they scatter off of Jupiter, and in one orbit, their orbit shrinks. So if you can sometimes just catch a subset of them as their orbit is shrinking. Like, that's what's going on for those comets. But it's a really, really tiny population compared to what we should be observing at 30 AU. So it's not even the mere existence of them, but it's the distribution of the perihelion distances that holds all the statistical power. Yes?
Have you hypothesized what the composition of this possible planet might be?
Yes, we have hypothesized. Of course, there's no way to calculate it, right? Like, we can calculate the mass of the planet, we can calculate the orbit, we can't calculate the phase or the composition. So the most plausible answer is that it is a building block of Uranus and Neptune. Right? Uranus and Neptune are planets, both of which are tilted, one by something like 30 degrees, right? Uranus is tilted by 98 degrees. That kind of tells you that Uranus and Neptune were built from smaller, planets that collided together. And in fact, the simulations of Uranus and Neptune formation tell you that the best way to make them is to have a bunch of 5 Earth mass objects collide. That accretion process is not 100% efficient, and many of these 5 Earth mass protoplanets, proto-Neptunes, if you will get scattered out by Saturn, okay, and kind of park in a Planet 9-like orbit. So the best guess is that this is a ice-rich object, and naively, and naivety is the key here on my end. You can say, well, if it's the same stuff that made Uranus and Neptune, then it should have a hydrogen helium atmosphere. That's good for observing, because if you have a hydrogen helium atmosphere, then you kind of have a bigger radius, it reflects more. But I've also done some calculations which might hint at the fact that even if it did have a hydrogen helium atmosphere, it might have lost it. So all I can do is speculate. So my best guess is that it's a Neptunian-like composition with a huge error bar, and the error bar covers pretty much all other possibilities with a large confidence. You know, the composition question is also interesting because there have been discussions in the literature about whether this is a planet at all. Now, if you think about it, the planet is the kind of stupidest, most boring answer. Right? Boring answers are usually correct, so that's kind of the place to go first, but it would be cool if it wasn't a planet. And there's a paper that suggested that, in fact, this is a primordial black hole that is bound to the sun. That would be awesome. There's no way to detect such a primordial black hole because the Schwarzschild radius is actually 10 centimeters. But one can dream, yeah. Yes?
Can you speak a little on the large eccentricity, since I think most of the giant planets have fairly small eccentricities?
Yes.
Does that imply this has to form at a different time than the other giants?
Let me answer that with this. Okay, so the way to think about why this would have a large eccentricity is that I think the most plausible formation path is the same as how you make the inner Oort cloud. Like, you can think of Planet 9 as just a massive inner Oort cloud object. So suppose you have Uranus and Neptune, Jupiter and Saturn, which you undeniably do, and a population of 5 Earth mass objects that are grinding together, creating Uranus and Neptune. Some of them get scattered out, right? Occasionally, a Planet 9-like thing would develop a highly eccentric orbit, but before it would get out, it would get perturbed by passing stars while in the cluster and park on some orbit like this. Okay, I'm telling you this as if it's a fairy tale, but there are simulations that support this fairy tale. And then the cluster goes away, and you are left on this mildly eccentric long period orbit. In fact, some of the best simulations of this particular process are not done by me or my group. They're done by Andre Zadoro and company at Rice University. They have really nice simulations that not just make something that looks like Planet 9, but by building Uranus and Neptune, they create the Planet 9 without knowing that it should be there. So, and they do so something like 40% of the time. This is unpublished, this is what Andre told me, but I think that's kind of the most plausible formation scenario. I don't think it formed in situ. I think you had a question?
Yeah, do you have an idea of what the mass range could be here?
Yeah.
Are we talking about Jupiter type or small round dwarf size?
No, so 5 Earth masses. Yeah. Neptunian dwarf. Yes?
But on that note, how well constrained is that mass or the orbital parameters? Change them quite considerably and still?
Yeah, so, okay, the question is how well constrained are the orbital parameters? Different ones are constrained to a different degree. The mass, we know, should be about 5, at most 7 Earth masses. It has to be greater than 4. So we know that relatively well. The reason we know that is because mass controls the kind of degree of confinement. Okay, if you crank up the mass, you over-confine the outer solar system. If you make mass too small, then the lifetime of the solar system is not enough to carve out the data set that we see. Now, there is a trade-off between orbital ellipticity and the semi-major axis. So you can play a little bit on that number, and that roughly corresponds to the preservation of the perihelion distance at about 250 AU, but not exactly. But again, there is less than a factor of 2 range in which you can play around. And inclination is the same thing. Like we don't know if it's 20 or 21 degrees, but we know that it's not 30, okay? And we know that it's not 10. And the reason we know that it's like if you crank it up too high, then you over-generate the kind of perpendicular orbits. And if you crank it up too low, then you don't tilt the Laplace plane of the outer solar system enough. So these are all constraints that came out of about 10,000 simulations, but cumulatively, it's starting to kind of form a coherent parameter range. So because of this, I also want to be clear. If LSST comes online and finds like a one Earth mass planet at 150 AU, like I will claim 0 credit for that. Like that is a planet, but it is not the planet 9, right? This thing that I'm talking about is defined by the specific dynamical processes through which it shapes the kind of outer solar system architecture. So that's why those numbers are relatively well constrained. Yes? Yeah. So there's, like, I would argue there's not an awesome one. There are lots of bad ones. Okay. Well, not bad, just not good. Yeah. So I would say, one idea that's floated around the literature quite a bit is that all of this is a detection bias, right? Like this is all not to be believed. It's all observation bias. We don't know for sure. First of all, you can calculate it, right? And as I said, I want to be honest, there is a chance that, for example, for the clustering, right, the statistic is about false alarm probability of 0.2%. Now, that's not quite 3 sigma, but it's 0.2%. For the Neptune crossers, it's like 5 sigma, right? So I would find it, I know that I already mentioned the deep state conspiracy, but I would find this to be a true deep state conspiracy if all of these different populations of the outer solar system, planetoids, pointed to the same planet and all turned out to be the consequence of different observational biases. Because remember, they're all found by different telescopes, by different groups. Like that would seem to be a remarkable consequence. A way better, like that would be arguably more exciting than the detection of Planet 9 because that would be like, wow, like how did that happen? There are other ideas like modifying gravity. Okay, there are ideas about like what if gravity does not work the same way at 2000 AU as it does in the solar system. And in general, like modified Newtonian dynamics, is a thing that floats around in galactic literature. Turns out, when you put that to the test, even though that's been suggested, right, if you really do the calculation correctly, it doesn't work, okay? Because you mess up other parts of the solar system, like the Oort spike goes away, you mess up the planetary orbits. Others have said, maybe this is not a planet, maybe the Kuiper Belt is cumulatively massive, okay? And it's actually the self-gravitational dynamics of the Kuiper Belt that's kind of self-shepherding. Again, right, we did the calculations properly with the GPU-enhanced n-body code that can handle that problem correctly, and it turns out it doesn't work. So I never want to be pathological and kind of believe myself too much, right? When other ideas come along, I try to go through the exercise of not ignoring them, but actually doing the calculation, maybe in some cases better than the proponents, to see what it really looks like. So I think I would argue that one of the remarkable things is that there isn't a good alternative theory. For most astrophysical problems, right, like the moment there's some data, right, there's 25,000 theories, put together by only 12 people, right? And so, in this case, there isn't really a compelling alternative explanation. So it's a little odd. Yes? Uh-huh.
A large part of that orbital period would be other brain
Yeah, well, first of all, I'm an optimist, okay? So there's that. Second of all, even if it's at the outermost point in its orbit, it's like the best it can do is maybe magnitude 26, 27. So that's out of range, but not, horrifically out of range. We've detected magnitude 26 objects before. So it might just be, and there's also enough of the orbit that is within range of the Chilean telescope. So it's not so helpless, right? Or it's not so bad. So I think there's a reasonable chance that LSST might find it. If not, there's a reasonable chance a follow-up survey might find it. Also, if LSST doesn't find it, we have to look for it with maybe a different technique. We're definitely not giving up, especially if LSST and other surveys confirm all of the indirect lines of evidence, right? Then you know that gravitationally something is there, right? So just got to keep looking, okay? And then maybe it'll turn out that it's not a planet or a black hole, it's just a giant alien mothership, okay? Just waiting to be discovered. Yeah. Yeah. Yes, you have a question?
Yeah, have you ever thought of putting the actual data in and then running your code backwards to see if you can figure out where it is?
Yeah, putting the data in and running it backwards, that sounds like a good idea, but it doesn't work because gravity is time reversible. That's literally no different than just saying we have all the evolutions and we reverse the direction of the velocities. It is, in fact, chaos, the gravitational chaos ensures that that calculation is the same as saying, let's, take senses of all the molecules in this room, reverse their directions, and then find out where each one came from, right? It wouldn't work. Entropy increases. So unfortunately, we can't do that game. The other reason we can't do that game is, as you saw in the simulations, particles get lost, they get ejected. And so even if you reverse time in the data set that you have, those particles that ejected never come back, right? So there are multiple reasons why you can't do. It would have been awesome if we could, though. Yes?
Was Percival Lowell just lucky that Pluto was discovered eventually?
Was Percival Lowell lucky? In a way, he was, his story is a remarkable one, right? He was lucky that he grew up in a wealthy family and was able to kind of establish the Lowell Observatory. He, his prediction of Planet X was not, was based, in a way he was unlucky, okay? Because his prediction of Planet X was based upon the residuals in the Uranian orbital motion that remained even after the detection of Neptune. But the only reason those residuals existed was because Neptune's mass was not known to high enough precision, okay? So the thing that he was chasing down turned out to be an artifact of not knowing Neptune's mass. And he was very passionate about this, right? Now, he of course died in 1916 and Pluto was discovered in 1930, but because they were looking for something of 7 Earth masses, right, they kind of found something and Clyde Tombaugh kind of assumed that that's the thing that they were looking for because it was kind of in the right part of the sky. And it was also very bright, okay? But Clyde Tombaugh immediately realized that there was a problem because he couldn't resolve the disk of the planet. And he thought, okay, if it's really 7 Earth masses, I should be able to see the disk. Instead, it looks just like a bright point source. So Clyde Tombaugh said, well, maybe it's 1 Earth masses. Okay, that was the answer because there's no way to measure mass. And then there's a great plot that you can make of the mass of Pluto starting in 1930 as a function of time. And it just reduces. And there's a paper from the 80s that actually predicts that Pluto would go away sometime in 2006. So they predicted the demotion, because that's where if you fit a curve, it crosses zero. And it was really in 1978, I think, when the satellite of Pluto, Charon, was detected. And because now if you have a satellite, you can calculate the mass, and people realize, oh my God, Pluto is 500 times less massive than the Earth, right? It's a tiny thing. The only reason, like, Clyde Tombaugh was able to detect it in 1930s, because in 1930, it came to the closest part of its orbit, but it's really a member of a much larger set of orbits, right? It's a member of the Kuiper Belt where other massive objects also live, like Eris, Makemake, Haumea, et cetera. In fact, my partner in crime, Mike, discovered many of the other large objects. So, lucky in a way, unlucky in another, but, interesting in all cases.
No more questions? Let's thank our speaker again.
Thank you very much.